I'm actually interested to go over. But so when I was online, I was going to class, and the way we taught, I mean, I couldn't figure it out, but I looked at a different way to just equal them to each other. Is there a reason we didn't learn that way,
Yeah,
or
it's
is
a
that the
lot
same?
more algebra.
Okay, I was like, this is so much easier for me. I told you when I look at it, it's like an algebra problem. That's probably why it works
Yeah,
out.
I mean, you can make this big ginormous formula and stuff, but
Mm,
it's kind of complicated.
gotcha, gotcha. All right.
Okay, let's get going. We got a lot of stuff to review today. We're going to review the cup of tea problem from homework 13. I observed and heard some students saying, "Oh, well, how do you deal with this one?" Well, we'll go through it. We'll solve it all the way through just to reinforce. And you're going to do some clicking along the way. And we're going to start with a clicking calculation, in fact. But before we do that, let me just remind you, office hours are Wednesday at 11, room 158 in the Physical Sciences building. SI today, 12:30, and then Monday at 4. So you're going to have a new homework assignment, homework 14, I guess, over the weekend. So you have plenty. You won't have it for today, but you'll have, if you go to SI Monday, you might be able to work on it. Now, let's do the cup of tea with honey, homework 13, number 2. And we'll just work it together. All right. So if you felt like you got caught napping on that one, or on the first one, substance R and substance H, fine. Just go ahead and take notes on this. So here we go. Here's the problem. Fixing up a cup of tea, putting in some honey. Now the specific heat of honey is different than the specific heat of water. All right. So this is two different substances. Honey's a little bit easier to heat up. And on this problem, just so you know, it's a little bit different from the substance R, substance H, with the beaker and the styrofoam cups and stuff. This one, the mass of the tea, in this instance, 267 grams. Better go ahead and write that down because we're going to do these calculations together. The mass of the tea is 267. Specific heat is 1. That's one of the variables, the mass of the tea. And then one of the other variables is the mass of the honey. All right. And so they're just random numbers, randomly assigned every time you take a new attempt. And then the other thing that varies each time is the temperature of the tea. The honey is fixed at 277 to start. Now I could have made that variable too, but I wanted it to be, somewhere close to a refrigerator temperature, so I just set that to 277 and let it go. Specific heat is 0.64. So those are the things that we got to deal with. So in this instance, the mass of the tea is 267 grams. The specific heat is pretty much the same as water, because tea is very close to water. It doesn't look like it, but its thermal properties are pretty close. So we just call it 1.00 calories per gram Kelvin. And in this instance, this attempt, it's 351 Kelvin to start. So that's the hot substance. Here are the specs for the honey. The honey is 158 grams in this instance, and the specific heat is 0.64. Now these specific heats don't change. All right, so every time you do one of these tea and with honey problems, you're going to be using 1.00 calories per gram Kelvin for the tea and 0.64 calories per gram Kelvin for the honey. Now this one has an initial temperature of 277. Now the initial temperatures are important because the way to do this well, I don't know, you may think that making out a whole lot of different tables or doing a big algebra formula is good, but the temperature gap, 74 Kelvin in this case, is important because you can get the equilibrium temperature in one move, actually 2 moves. So that's pretty efficient. So the temperature gap is 74, and that's from 277 up to 351. Now they start out, they're not in equilibrium. So there's going to be thermal transport between the tea and the honey. The honey's going to warm up, the tea's going to cool down. All right? And that gap is going to close. And every exchange of a single calorie is going to cool off the tea and warm up the honey by a certain amount. Now we're about to figure out that amount. All right? So let's do that exchange calculation by exchanging plus or minus 100 calories. Now there's nothing special about plus or minus 100. If you have a big object or a set of big objects that are interacting thermally, you might want to use 1,000 or 500. Or if you're, working on a really big assembly, you might want to talk about a million calories or more. But for this is fairly small. So 100 plus or minus 100 calories is not outrageous. It will work. All right, so let's do that. Let's try exchanging that. So, and let's do it for the tea. So here's how you do it. You say, all right, my Q for the tea is cooling down, so this is negatory. It's minus 100 calories. But as I said, you could try it with minus 500 if you felt lucky, and actually 500 would work nicely in this one. 100 is a little bit small, as we'll find out. But anyways, you use MC delta T on the other side. So that's the mass of the T, the specific heat of the T, which we both know. And then delta T of the T, that doesn't sound good, especially spoken. The delta T of the green tea, we'll assume it's green tea, we don't know. But we know the mass of the specific heat. So if you plug those in, here's the plug-in step. All right, 267 grams for the mass and 1.00 calories per gram Kelvin for the specific heat. And then the unknown, delta T, is still a symbol. So if you look at that second equation there, yeah, you've got everything you need except for delta T. So that means you can solve for delta T, get it by itself, do a little bit of algebra and multiplication stuff, and you're golden. Now, let me point out to you, at this point, you can, on the right-hand side, you can cancel grams. Do you see that? The grams in the numerator of the first parenthesis and the grams in the denominator of the second parenthesis. All right? So those cancel. And actually, left and right, calories cancel. And so you're basically left with a Kelvin in the denominator on the right side there. All right, so that's, but I'm not canceling the calories yet. I'm going to leave. So here's your, I'm putting my two parentheses on the right-hand side. I'm putting them together. This one's cinchy. 267 times 1.00 is just 267. And I've canceled grams. So on the right, I have calories per Kelvin in that first parenthesis. And then on the left, I haven't done anything with the calories over there yet. All right? But I'm going to do that in the next step. Let me pause for questions. Yes? Uh-huh. No. That's not going to, if you put the temperature gap in for Q, that's mixing apples. You must have gotten it accidentally correct. I don't know. I didn't know that was possible. I mean, so for the first one, right? Because the first one is 1100 Kelvin and 1000 Kelvin. The second one? You got it right? Get out of town. I'm going to have to check that out. What is your last name? Really? So it's a total luck shot. Unless you're maybe describing it differently than what you actually did. But come talk to me after lecture. I want to double check your attempts just to see how, because I'm not saying that you're wrong. I'm just saying if it's really true that it's a total, luck shot. But that's good, And other people probably had a similar set of numbers. So, anyways, so here we go. We have minus 100 calorie. We're cooling down by 100 calories, or we're losing 100 calories. 267 calories per Kelvin in the first parenthesis on the right, third equation block, and then delta T of the green tea mixture. All right, so we can divide both sides, if you please, by 267 calories per Kelvin, which is what I've got there. All right, and now I didn't put the little slashes, but you can mentally slash out calories here. Now, the reason I left it here is because the calories in the numerator and the calories in the denominator cancel. But the Kelvin on the left side here is in the denominator of the denominator. So that means it flips up to the top, to the numerator. And so, which is what you want. You want the kelvins in the numerator, and it works out to negative 0.37. Can you verify me on that? Negative 100 divided by 267. Just double check me on that. Should be negative. Anybody verify me? You got it? Anybody over here? Yeah, get your calculators out because we're going to be calculating. You're going to be doing the honey in a second. Okay, so you're going to be doing all these steps. All right. So let me pause for questions. Okay, let's keep going. Now, so we exchanged minus 100 and plus 100. And we didn't do the plus 100 yet, but we're going to do that. You're going to do that in a minute on iClickers. But here's the bottom line. When you drop 100 calories out of the tea, the temperature of the tea goes down by 0.37 kelvins, right? Now we're going to use that. It's not, we got a gap of 74. So, 37 times 2 is 74. So, but the thing is, delta T for the honey is not going to be the same size. So we're just going to have to calculate that one. But at least we know for the T, we drop in 0.37. Now, here's an IQ test for you. It's not an iClicker, but mentally ask yourself, if I had exchanged minus 1,000 calories, what would my change of temperature be? In other words, 10 times that amount of energy. Not 37. Negative 3.7. It'd be negative 0.37 times 10. So sometimes, using the right delta Q, plus 100, plus or minus 100, or plus or minus 1,000, sometimes it's kind of handy, Anyways, so the new temperature here, now write this down, the new temperature of the tea, it started at 351, and now it's just down to 350.63, so it hasn't budged by much. Now what that tells you is we're probably going to have to exchange a bunch of 100-calorie bindles of energy. And what it also tells you is plus or minus 100-calorie bindles are too small for this problem. But we'll make it work. And I'm going to show you how to make it work. Okay, so the basic formula here is your new temperature is whatever you started with plus your delta T. Okay? And in this case, the delta T is negative, so it's like a subtraction. Okay? 351 minus 0.37. All right, now let me pause for questions. Yes? It's right here. I just mentioned it. We started at 351. We subtracted 0.37, and we're down to 350.63. Good. Yeah. So unfortunately it didn't budge by much, but we can still make this work. Now we're going to do the same delta T subscript H for honey now, and you're going to do it on your own. Now this is the same kind of calculation, but using honey and using plus 100 calories, right? Because the honey warms up, right? So here we go, and let me start the question. Okay, and this is a numeric question. So type in your number to the nearest 0.01 Kelvin, and then hit the send key. All right, and just take a minute to do this. And it's the same calculation, except you're doing it for the honey, and you're using plus 100 instead of minus 100, because the honey's warming up. Oops, wrong clicker. Go nitro. All right. So this is a boring slide, but I'm going to be putting the calculation up here in the blank area as soon as you guys are done. So don't give me the new temperature, give me the delta T. Because I see one person here with the new temperature. It's right, but that's not what I'm asking for. I'm asking for delta T of the honey. Round it off to the nearest 0.01 Kelvin. Don't give me a whole number. You guys are doing good. Okay, and it's not negative, it's positive. The honey is warming up. Starts in the refrigerator, so when you put it into hot tea, it's going to warm up. And they're both going to level off at a certain temperature when you drink it. All right, we got 2 minutes going here. Do not give me the new temperature. Do not round off too much. I want something point something something. I don't want less than that. Okay, 1 minute. And hey, you guys, this is a real brain burner. So, but you guys are doing pretty darn good here. At least this part. It's a brain burner because it's a difficult problem, and there's a lot of different ways to solve it, and they're all rather complex. So this calculation is just one of several sub-calculations that you have to do in order to figure out the equilibrium temperature. Okay, which was what you had on the homework. 30 seconds. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, make sure you hit the send key. Otherwise, I won't have your answer. All right. Good. All right, let's look at the calculation. So take some notes. Here's your first move. 100 calorie equals MC delta T. And figure out delta T. Now this is delta T for the honey. So this is going to be a positive number. Everything in here is positive. For the T, that's cooling off, so delta T is going to be negatory. And that's why we start with minus 100. All right, here's your plug-in. Now 158 grams, that's the mass of the honey, and its specific heat is 0.64 calories per gram Kelvin. So this is not going to be a cinchy one, but it's still pretty easy. You know, those first two parentheses multiply out to 101.12 calories per Kelvin. Anybody verify me on that? Remember that coming up? Raise your hand if you verify me. Okay, good. Yeah. All right, so now so we're going to divide. So this is going to be about 1. It's going to be a little bit less than 1 because my numerator is 101, my numerator is 100, the denominator is 101, and it works out to 0.99. And a good fraction of you guys got that. All right, now let's type out the new temperature. 277.99. You're almost up to 278. Right? So this is still kind of a pokey calculation, but we're going to leverage it, you know, out the wazoo and get this thing solved in our next move. All right? So here's what happens. When you exchange 100 calories from the tea into the honey, the tea cools to 750.63. Is that what it was? No, 350.63. And the honey warms up to 277.99. Now, we still have a temperature gap. Right? So here's what it looks like. All right. Up here, let me go to the cursor now. Up here, here's my first exchange. Okay, so the 351 cools off to 350.63. And then down here, my 277 for the honey warms up to 277.99. So, you know, you could draw a big table like this if you want. And this was going to be ginormous. Because, and that's why I have ... up here. I mean, here's the second exchange of 100. You get up to 278.98. And then this one gets up to 350.26 or down to 350.26. So we're still kind of inching closer, but you know, it's still, we still have a big gap. All right. But no matter what, you know, so this one is, you know, let me do this with my clicker. So this one's down another 0.37 to 350.26. And this one's up another 0.99 to 278.98 kelvins. And in past semesters, we would just build this table up and just keep clicking and you know, grinding it out, which you can do, you know, if you feel like doing that. And the reason I like the table like this is because nature is like this. Nature, it doesn't. This is what we call the arrow of time, the thermodynamic arrow of time. Did you ever hear that, Daniel? We think about the thermodynamic arrow of time in the theory of relativity with black holes and stuff. The passage of time, there's only one way to understand this table. Time is flowing towards from the top downward on the left side over here. So time flows this way to equilibrium. And over here on the right side, time flows upward. And so physically, so I was just thinking about, you know, this is a good example of that. Nature doesn't do it the other way. It doesn't flow, you know, temperature, energy doesn't flow from the cold one into the hot one. It only flows from the hot one into the cold one. At any rate, you're going to need a bunch of exchanges, okay? And each closing the gap by, 1.36 total. So closing it by 0.37 from above and 0.99 from below, total of 1.36. So make a note of that you close the gap by 1.36 Kelvin every time you exchange, plus or minus 100 calories. Right now, we're going to use that in the next clicker question. Hit your refresh key, if you please. I can't do my clicker. I have a boop. I got to pause the podcast here for a second. I found something. Come on, clicker. And this is a multiple choice. So hit refresh and then and you'll be able to answer this. So we've got a total energy gap of 74. So we're backing up to the beginning now. And every time we exchange 100 plus or minus 100 calories, we cut that gap by 1.36. So how many times are we going to have to exchange? Plus or minus 100. Right now, I want you to think. Come on, baby. My clicker's not working here. Oh, hold on a second. I can't get this thing to advance. Let's see if we can get this to work. All right. All right, here we go. So we're going to leverage this in the next. Here we go. Here's the problem. All right, so think carefully, and there's your 4 options. Now you can start clicking. Well, I don't know how that happened. That was audacious. I can't believe this thing. Dr. B. All right. Well, go ahead and type in your answer. 15 seconds to type it in. I just gave you the answer. You better get it right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, stop. Yeah, you guys did good. So here's your strategy. The number of plus or minus 100 calorie exchanges is basically the size of your gap divided by how much closer you get per exchange. So in this case, it's 74. That's my initial gap. And every time I exchange 100 calories, I close it by 1.36. So if I divide 74 by 1.36, that'll tell me how many exchanges I need. Now, the nice thing here about using 100 is, instead of using 20 or 27 or 509 or some weird number, if I see 54.4 exchanges and I know each one of them is 100, all I have to do is say, all right, this much is my total, 54.4 times 100. So 5,440 is my total energy exchange. Now make a note of that. We've used what we calculated with plus or minus 100 to figure out the total amount that's going to be exchanged. All right? Because we used what we figured out, 0.99 and 0.37 to figure out the closure, and then 54.4 of those will close the gap all the way to equilibrium, right? So let's see if I can do this right. Boy, this one was blooped up. But let's go to the next slide. So here's the second move. Once you've figured out this number of exchanges that you need, just do it. So minus 5440 calories, MC delta T for the T. And then positive 5440 calories, MC delta T for the honey. All right. Now you can do either one of these and get your thermal equilibrium temperature. We're going to do both just to verify. And we did a little bit of rounding off to get 54.4. So our answer is going to be a little bit off, but still pretty close. Close enough for government work. So let's do it. All right. So 267 is MC for the T. And remember, 101.12 is MC for the honey. That doesn't change. Kelsey. Yeah, good question. Round it at the end. I usually try to round it at the end, but I put in a plus or minus in the answer box for you guys. So if you round it off a little differently than I do or than the Canvas does, there's still a little bit of plus or minus. And the two homework assignments, I think it was plus or minus 0.2 Kelvin. So so for something like this, where you're doing some estimation stuff, I have to put in a plus or minus. Daniel.
Yeah, I noticed that for this homework, I noticed that some people they round it after each step, and they're
yeah, that's gonna don't.
People actually ask me like why, like they did the problem correctly, but they didn't get the answer correct because
They were too far. They were near it though, right?
I'm sorry.
Were they near the correct answer?
Yes, they were close,
but not enough to get in the plus or minus 0.2 Kelvin. Yeah, so don't round off until you get to the end of the problem. Just carry a bunch of extra digits. That's what I usually do. All right, so divide by 267. And that means the total change of temperature for the T is a cool down by 20.37 Kelvin. All right, from 351. So this is going to take us down to about 330 point something. Now over here for the honey, positive 5,400 calories divided by 101.12. And that works out to 53.80 calories, or Kelvin, I should say. And that's going up from 277. So let's figure this out now. Okay, equilibrium temperature, the initial temperature for the T, plus its delta T. So 351 Kelvin initial plus negative 20.37. And notice that I have the minus sign inside the parenthesis. All right. But it's just like a subtraction. So, add a negative is the same as subtraction. So, right. And so that works out to a certain temperature, 330 point something. And then this one, the thermal equilibrium, if you do this side, it's the initial temperature of the honey, 277, plus 53.80 Kelvin, all right? And so now we've figured out both of these, they better be consistent, all right? So 351 minus 20.37, 330.63. Okay, so that's about right. It's about 20 point something below the initial. And this one's going to be almost 54 above the initial. So if you do the thermal equilibrium temperature from this side, you get 330.8. And you can see here, Kelsey, that these two are are separated by about less than 0.2. So we're good. All right, now if you were going to type this in to the nearest tenth, 330.6 and 330.8 would both be righteous. Okay, and I think the really accurate is 330.7. But if you're going to type it in as you will on a test, or if you do have it on a test, I'll probably just put to the nearest Kelvin, make it a little easier. Okay, and so this one, and so you can see to the nearest Kelvin, we agree. Both calculations agree. So you can do the one on the left and you're done. Or you can do the one on the right over there with a positive 5440 and you're done because they come out to the same thermal equilibrium temperature. But if you do both, of course, you can check, and that's why we did both. So we come out to 331 Kelvin approximately to the nearest whole Kelvin. Question? That's what I did, 54.4. And if I'd gotten 54.42, I kept another digit, that might make it a little bit more accurate. You know, whatever the extra digits were, I can't remember what they were after 54.4. Yeah, but I mean, you can, yeah. And so if you estimate it to the nearest calorie, or if you multiply and keep enough digits to get the nearest calorie, then yeah, that's not a, so that would be, take your exchange tally, 50, and so go 54 point something something, multiply that by 100, and you'll have a whole number, okay? No, I don't. I just, because, I kept it to 1 decimal point, so I went 5440, and that 0 was, a placeholder. And I got pretty close, 330.63 Kelvin versus 330.8. That's not too bad, but you can go out to the 100th place and then but see, the thing is, what if you choose something other than 100? What if you choose 1,000? But we could have chosen 1,000 on this. That would be 10 times bigger, so we would have had 5.44 exchanges. All right, if we'd gone with plus or minus 1,000. Do you agree with me? Yeah. So, anyways, I'll give you another example of this on the homework. I might give you the T problem again, and you'll have fresh numbers with it. So, now I want to talk about oscillation and waves, and we got a good amount of time. Let's keep going with this. Now, this is chapter 6 in the textbook, if you have the textbook, which is optional. But let's, look at this wave. This is over in Portugal, at a place. Now, what's this place called? I think it's called Nieves, Portugal, and it's this beach where, when the wind conditions and the weather is right, you get these ginormous waves. Now, look at this photo. See, these up here, this building, let me get my cursor over here. So these guys right next to the lighthouse here, here's a little tiny lighthouse, right? And this is up on a cliff above the beach, right? And these are humans, so maybe about 5-6 feet tall, right? Now this little thing down here, where my cursor is, that's a man on a skateboard, a very brave man. Now, so he's maybe 5 feet there because he's crouched a little bit, right? Now, mentally estimate how many copies of him to reach the top of the wave, and then how many copies again to get down here. There's the bottom of the wave, and you can see that's a big, big wave, big, big. You can't even see the bottom of it. You can't see the beach. Can you imagine the rush? Oh my God. I've done a lot of things in my life, but I've never done something like that. All right, now, so we're going to be talking about waves and oscillations, and that's a good example of a wave. It's more like a rogue wave out in the ocean. Now, circular motion, we've talked about that. One of the ways to think about it is break down the horizontal and the vertical, the X and the Y components, into two identical oscillations. So if you take a point up there, like somewhere on the first quadrant, for the and map it out, that's the X and the Y coordinate. Then the X coordinate is going to look like this if you plot it out on on a graph paper. So on that graph, time is horizontal and the X coordinate is vertical. And it goes up and down like a wave in the ocean. So that's oscillatory. It's not a wave, but it looks like a wave in the ocean. Kind of. I mean, the waves in the ocean aren't that steep, but not normally anyways. Now the same thing holds for the Y component. Right? So the vertical component will look like this. All right, it'll be the same size. So this is 300 pixels left and right. And so it goes 300 to the, this part, let me get my cursor over here. Okay, up here, the top of the first bump on this X graph, that's 300 pixels to the right. It's positive X. And then down over here, that's 300 pixels to the left, negative 300 pixels. So that's when it's over here. Okay. Now, over here, the Y component starts at 300, all right, and it goes to 0 right here. Okay, so that's when it's crossing the horizontal axis. And then here it is at negative 300. So here's negative 300 on the Y axis. Here's positive 300 up here. All right. Now, I'm going to ask you some brain burner questions, multiple choice, and hopefully this thing will work properly, unlike last time. All right. Now, remember, this graph over here tells you the X component as a function of time. And this one down here, the vertical component, or the Y component. In other words, the Y coordinate of a point on the circle, if the, if the point represents the location of an object that's moving on the circle, right? And the horizontal axis of each is time. So just to reinforce that, the top half of these graphs is a position to the right of the y-axis. And, oops, let me go back to that. And the lower half here is to the left of the y-axis. Now here on the y component, the upper half is the top half of the motion. So the top hemisphere of that circle. And then down here, when you see the red line down here, that means it represents a point down here in the southern hemisphere of the circle. All right. Now, you don't have to hit the refresh key unless you want to. All right. Now, this is it's kind of a brain burner. I want you to look at both of these graphs and interpret them for the starting coordinates. Okay. It's the starting coordinates. When t is equal to 0, what are the x and y coordinates? All right, now let me start this question. Okay. You can type in your answer now. A, B, C, or D. Yay, it's working. Okay, and this one is the x. The black graph is the x component, and the red graph is the y component. Okay. 30 seconds. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, so there's the starting point. So on the at t equals 0, the x coordinate is equal to 0. But at t equals 0, the y coordinate's all the way up here at 300. So that means that option A is correct, and most of you got that. So that's good, all right? And that's a interpretation skill. So we're trying to coordinate this picture as a motion track and those graphs. All right. So it starts up here, and then later in the first cycle, it's over here. So that tells you the direction that it's going. So let's think about this. Is it clockwise or counterclockwise? So here, let's go back here. Let's look at this. Next question. Multiple choice. Is it clockwise? Is it impossible to determine? Or is it counterclockwise? So this is kind of a mental interpretation. Problem. $15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let me see what you guys did. Yeah, pretty good. Let's take a look at it. After the first cycle, here's what you got. You're back here to 0, but you're coming in from the left. And up here, you're back at 300. You're back at the top of the circle, but you're coming from the right-hand side of the circle. So what that means is you're definitely going to be, and here's the first part of the, here's the coordinates of the first point with the black diamonds here. So this thing's definitely clockwise. Most of you got that. So the bottom line here is these coordinate graphs over time, they actually encode the velocity, the speed, and you can actually get the direction counterclockwise in this case, or excuse me, clockwise in this case. All right. Now, we're going to be looking at these graphs from time to time, but let's get down to some concepts. Why do physical systems oscillate? I mean, the weather is oscillates. There's this thing called El Nino. You've probably all heard of it, this weather pattern. And the fancy word for it is something southern oscillation. It's an oscillation in the atmosphere. No, it's an oscillation in the currents of water in the Western Pacific that generate El Nino. So it's kind of, it's a lot of different things can oscillate. Simplest example, though, is a spring. Okay, now the force law for a spring is basically that the force depends on your displacement from equilibrium. Equilibrium? Yeah. That's becoming a more and more important concept. Okay, so the force is proportional to x. So if x is the measurement of how far you are left or right of equilibrium, then that distance, the more you have of it, the more force you have. Okay, either push or pull. And its direction is opposite to the direction of the displacement. So what that means is you have a restoring force. Okay, so if you're actually at equilibrium, so if this is the equilibrium position, let me get my cursor over here, right here at x0, when you're over here, when you're right at x0, you're not going to have any push or pull. Okay, but if you pull to the right, Okay, so no push or pull if you're at equilibrium. If you go to the right of equilibrium, and that's the second diagram down here, so right now the position x is greater than x0, the force is leftward. The spring is going to pull back on that mass to the left, back towards equilibrium. And then if you're to the left of equilibrium, which I haven't sketched, but if you think of this red block here as being over here, somewhere to the left of equilibrium, then you can think of the spring as pushing back to the right. The spring is compressed. And the place where there's no compression or extension is equilibrium. So this first picture, this first diagram here, the spring is at its equilibrium position. There's no push, there's no pull. There's no compression force, there's no pull force back to the left. All right? So the formula for the spring force is simply this: F equals minus kx. And as a side note, it's not in the outline here. K is called the spring constant. Right? Spring constant is K. So the minus sign means opposite direction. X means displacement from equilibrium. And K is a constant of proportionality because X is just meters. And for a force, you need kilogram meter per second squared. So K is a constant. And students, the spring constant K encodes the stiffness of the spring. So if K is big, that means it takes to squeeze the spring down by 1 centimeter requires a lot of newtons. Or to extend it by 1 centimeter requires a lot of newtons, compression or extension. But if K is small, it's cinchy, like a slinky. Slinkies are very easy to stretch. Okay, it doesn't take many newtons to stretch them at all. But like a car, in a spring in a car, those are designed to support tons worth of metal, and so they have to be really tough to stretch, really tough to compress, and they are. I mean, you could take a car spring and try to squeeze it. You'd maybe get a millimeter even with you and your friends. The potential energy function is spring potential energy, SPE, 1/2 kx squared. Now, for those of you that have had calculus, you might recognize that this is an integral of kx. All right. Raise your hand if you've had calculus class. A couple, 3 of you, yeah. So 1/2 kx squared. Now that's going to be, we're going to use that probably next week. But the formula for the force and the formula for the potential energy are important for us. The kinetic energy of that mass at the end of spring, that's still 1/2 mv squared. But the force on that mass is minus kx, and the potential energy of the mass is 1/2 kx squared. Question?
Can you go over the formula of negative kx?
Yeah, the minus sign means that it's opposite direction from the displacement x. So if x is positive, that means it's to the right, which is right here. Okay, so this one right here, x is to the, right over here. X is to the right. The minus sign then says, all right, I've got a positive, and k is always positive. So k times x is positive, and then the minus sign makes it all a negative, which means the force is to the left. Okay. Now, if you go over here, and I don't have a picture of it, but if you had the mass over here, k is still positive. It's always positive. But x is negative. So minus k times a minus, like 2 centimeters, that's going to be a positive. That means your force is to the right. Right? So the minus sign encodes the restoring force nature of the spring force. If you move it to the right, it pulls to the left. If you move it to the left of equilibrium, it pushes back to the right. Okay? And it always works that way. And at equilibrium, there's no force. It's an instant of time. So if this thing is going back and forth, there's an instant of time right at equilibrium where it doesn't have a leftward or a rightward force, but only for that one instant of time. Okay, does that help? Good. All right. Now here's what I want you to remember. Anytime you see a force that's equal to minus kx or minus k times some coordinate, or you see a potential energy that's 1/2 times k or some constant times the square of a coordinate, then it's going to oscillate, guaranteed. Right? And one of the interesting features of the electromagnetic field is that the electric field and the energy of the electric field is proportional to the square of the electric field and the square of the magnetic field. So that's why the electromagnetic field oscillates, because its energy is proportional to the square of the amplitude. Question?
So what does it mean to oscillate?
Like a spring. Bzz, 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 bzz. Waves in the ocean. Okay, it'll form waves, or it'll be described by those, those wavy coordinate graphs. Okay, the coordinate will be, in this case, it's the x coordinate, right? But the interesting thing about electromagnetic radiation is, it's not the position of the, there's no position for the wave. The wave extends to infinity, but the electric field E and the magnetic field B, they're the ones that oscillate, and that's why the speed of light is that's why the theory of relativity is what the theory of relativity is. It's very interesting. But let's keep going through the basics here. Now, oscillating system. What was your name again? Ariel. So here's a picture of something oscillating. It starts at equilibrium, and then it moves out to, let's say that it moves out to maximum extension. And then after it hits maximum extension, it's going to move back to the left, so it hits equilibrium again. And then it's going to move to maximum compression here. And after that, it's going to move back to the right, back to equilibrium. All right, so let's take a look at this. That's one full cycle. So it's basically 4 journeys to or from the equilibrium. So let's look at it. First part of the journey, from equilibrium to max extension. All right? Now at max extension, you got maximum force to the left. All right? Because your displacement is to the right. All right? So now because that force is to the left, when you're out there at max extension, you're going to start accelerating back this way. All right? So you have a force out there, so you're heading back to equilibrium. But guess what? Once you hit equilibrium, you're going to start getting a rightward force because you're compressing the spring. So, once you get, once you get here to equilibrium, you start rotating over here to the left, your force is going to be back to the right. So when you get to max compression here, you have maximum rightward force, and guess what happens? Bing, you start accelerating back towards equilibrium. All right? So those 4 arrows are the distances from equilibrium to either max compression or max extension. All right? And there's a fancy word for that in physics. Right? So all these things add up to one full vibration or cycle. Now, mathematicians and physicists are lazy. It's almost like a law. It's almost like a requirement. Especially they're lazy about doing math. So they decided that, since they have to do a lot of trig and calculus, it's easiest to call the amplitude of a wave the length of one of these 4 arrows, either any of these 4 arrows. So from equilibrium to max extension, from max extension back to equilibrium, from equilibrium to max compression, from max compression back to equilibrium, either one of those things. Okay, let me go back. I want to reinforce that. Okay, so the 4 journeys. And these arrows are all called amplitudes, or the length of the arrow is what we call the amplitude. The amplitude of oscillation for this spring system. And it's basically because of calculus and trig. You might not think about it, but using trigonometry to define these positions is actually pretty easy. And so let's take a look at waves in the ocean. So and guess what? I use trig functions to create this graph in a spreadsheet. It's pretty easy. Anyway, so here's a wave in the sea. Here's sea level. Okay, so draw sea level, and I made it a blue kind of a rough line there to represent the position of the water when the sea is calm, sea level. All right, now the red line shows kind of an idealization of a wave in the ocean when there's waves passing past this point. All right. So from sea level up to maximum wave height, that's the amplitude of the wave. All right. Or you could go this way, from sea level down to the bottom of the trough. Okay. Those two distances are the same. So either one of those we could call the amplitude. All right. So if you make a measurement of one or the other, you're good. All right. And the same for any of these other peaks. Oops. Same for any of these other peaks. Here, or this trough, or any other trough that you might have. All right, now, let's get back to the circle. The amplitude of the circle is the radius of the circle, or the amplitude of the oscillations of the x coordinate are the radius of the circle. Right? Now, if you have a perfect circle, the amplitude of the x oscillations will be equal to the amplitude of the y oscillations. But if you have different sizes, you'll have an ellipse, an oblong ellipse. So it's pretty cool. All right, so you start up there as we started in the previous slides, and you work your way around using those graphs. Now, I want to talk about waves for the last few minutes of lecture. Let's see, what time have we got here? Come here, baby. Okay, good. Let's talk about some basic wave concepts, because waves are actually what we need to understand the periodic table, which is why we're studying these oscillations. So the interesting thing about waves is they behave way differently than like a particle. When we think about Newton's laws of motion, we're thinking about the motion of particles or objects that behave like a particle. In other words, a baseball or a football or something. But waves are different. They transport energy and momentum across space-time. But waves that hit the shore in Cocoa Beach may have been generated by some storm off the coast of West Africa. But it's not water from West Africa washing up on the beach as those waves crash. It's water from the Gulf Stream. But it's the energy from Africa that's propagated across the ocean, across the surface of the ocean, that causes those breakers. So it's not easily localized. And another thing, waves behave differently, way differently than a Newtonian particle. So what waves do, baseballs cannot do. What waves do, billiard balls cannot do. BBs, bullets, all this stuff. Now the exception of this is a quantum particle like a photon. And we'll talk about that in a couple weeks. All right. Now, one of the things that waves can do is diffract. And they can also generate wavelets when they pass by a barrier or an edge of a barrier or an opening in a barrier. Now, here's what wavelets look like. Okay. The dark black line here is a barrier. Okay. Let me get my cursor over here. Okay, this dark black line here is the barrier, and there's a gap in the barrier. Now, these waves are coming in parallel to each other, and they hit the gap. Now, if they hit to the left of the gap, they get absorbed by the barrier. If they hit right of the gap, they get absorbed by the barrier. But if they go through the gap, they form wavelets, and it's like a whole new source of circular waves emanating from each point in the gap. Right? Those are called wavelets. And as a result of that, on the other side of the gap, the waves that were parallel in here are now circular, and they're actually diffracting. You can see a bright or a very strong wave action here, but you can also see over here to the left a little bit of wave energy. It's cutting to the left. What's up with that? You know, the waves coming in, they were just going straight up, but they hit that gap, they form wavelets in the gap, and then they diffract off into other directions. You can see it over here a little bit to the right as well. So that's one of the things that wavelets do, or that waves do. That, Newtonian particles don't do that. Now, there's a simple wave equation, V equals lambda F. We're going to work on that. Maybe do a calculation here if we have time. Right? So here's the wave equation. This is a generic wave equation for any wave system. V equals lambda F. Now, if you're studying waves in the plasma of the surface of the sun, the wave equation is going to look a lot different from that, but it can be boiled down to, approximately V equals lambda F. It's kind of nice. Now, what do those symbols mean? Lambda stands for the wavelength. So that's a Greek letter lambda, lowercase. And that's the spatial distance between two waves. So peak to peak or trough to trough, that's one wavelength. All right? And F stands for the frequency. Now, the period of a wave, capital T, is the temporal interval between waves. So if you're sitting by on a jetty out there by Cocoa Beach or somewhere, and you're timing the waves as they come in, they break on the jetty, like once every 6.4 seconds. Well, that's your period. That's your wave period. The frequency is 1 over that, right? So V equals lambda F. Lambda is the spatial distance, and frequency is 1 over the temporal distance, or the temporal interval between the waves. All right. Now, here's another picture of my diffraction field. And this one's nice because you can really clearly see diffraction. And, right here, look where my cursor is, right about here. There's no wave propagation there. In that direction, from the gap, if these were light waves, you wouldn't see anything. You'd see darkness, or you wouldn't see any light. But if you were looking in this direction right here, if these were light waves, yeah, you'd see something here. Whatever color the light was. And of course, right down the pipe here, right in the middle, you'd see the brightest of all. Right? So light is a wave in the electromagnetic field, which controls compasses and charged particles like electrons and protons. Now, the light forms a full spectrum. So let's take a look at a spectrum. Okay. Now, the shorter wavelength is down here to the left. So this kind of represents wavelength. And longer wavelength, big distance between peaks, is over here. Visible light is kind of in the middle. Gamma ray and X-ray and ultraviolet are fairly short wavelengths. Infrared is longer wavelength, and then microwave and radio are really, really long wavelengths. And visible is down here in the middle. Okay? Now, let's start with the letter C. Radio and infrared are the longer wavelengths. And then the visible is kind of in the middle. So I always use the word Roy G. Biv because that's the order of the colors. Red, orange, yellow, green, blue, indigo, and violet. Okay? It's almost like a name, Roy G. Biv. Some say that Roy G. Biv actually existed. but no, it's like, like the Flying Dutchman. It's a legend, but nobody's ever been able to verify the whereabouts of Roy G. Biv. Then above the Roy G. Biv visible, short wavelengths, ultraviolet, X-ray, and gamma rays. Now the speed of light is 3 times 10 to the 8 meters per second, right, which is 300 million meters per second. Really, really fast. And one way to think about that is the amount of time it takes light to go from the surface of the sun to our planet is about 500 seconds. So the distance, so we don't measure the distance in light years. Stars are measured in light years. But Earth from the sun, 500 light seconds, yeah. And light hours and light minutes are fair game for the solar system. Light years for other stars, and millions of light years for other galaxies and stuff. Now we're going to talk some more about this on Tuesday, but for the weekend, you're going to have some oscillation homework, and go ahead and study that and work on that this weekend. And I'll see you next Tuesday. You're dismissed.